Suppose you're in San Francisco and you want to go from Twin Peaks to the Golden Gate Bridge. You want to get there by bus, but with the minimum number of transfers. Well, here are your options. What's your algorithm to find the path with the fewest steps? Well, can you get there in one step? Here are all the places you can get to in one step. The bridge isn't highlighted. You can't get there in one step. Can you get there in two steps? Again, the bridge isn't there, so you can't get to the bridge in two steps. What about three steps? Aha! Now the Golden Gate Bridge shows up. So it takes 3 steps to get from Twin Peaks to the bridge using this route. There are other routes that will get you to the bridge too, but they're longer, like 4 steps. The algorithm found that the shortest route to the bridge is 3 steps long. This type of problem is called a shortest path problem. You're always trying to find the shortest something. It could be the shortest route to your friend's house. It could be the smallest number of moves to checkmate in a game of chess. The algorithm to solve a shortest path problem is called Breadthfirst search. To figure out how to get from Twin Peaks to the Golden Gate Bridge, there are 2 steps. 1. Model the problem as a graph. 2. Solve the problem using Breadthfirst search. This module introduces graphs. First, I'll talk about what graphs are, and I'm not talking about the ones with an x or y axis. Then I'll show you the first graph algorithm called Breadthfirst search, or BFS. Breadthfirst search allows you to find the shortest distance between 2 things. But shortest distance can mean a lot of things. You can use Breadthfirst search to do things such as write a checkers AI that calculates the fewest moves to victory, or write a spell checker, or find the doctor closest to you in your network. Graph algorithms are very useful. These are algorithms you'll be able to apply again and again. Like I mentioned earlier, the graphs I'm talking about don't involve an x or y axis. A graph models a set of connections. For example, suppose you and your friends are playing poker and you want to model who owes whom money. Here's how you could say Alex owes Rama money. The full graph could look something like this. The graph on the screen now shows that Alex owes Rama money, Tom owes Audit money, and so on. Each graph is made up of nodes and edges. That's all there is to it. A node can be directly connected to many other nodes. Those nodes are called its neighbors. In this graph, Rama is Alex's neighbor. Audit isn't Alex's neighbor because they aren't directly connected. But Audit is Rama's and Tom's neighbor. Graphs are a way to model how different things are connected to one another. Now let's see Breadthfirst search in action. In Unit 1, we looked at a search algorithm called binary search. Breadthfirst search is a different kind of search algorithm, one that runs on graphs. It can help answer 2 types of questions. The first type of question is there a path from node A to node B? The second type of question is, what is the shortest path from node A to node B? You already saw Breadthfirst search once, when you calculated the shortest route from Twin Peaks to the Golden Gate Bridge. That was a question of type 2. What is the shortest path? Now let's look at the algorithm in more detail. You'll ask a question of type 1. Is there a path? Suppose you're the proud owner of a mango farm. You're looking for a mango seller who can sell your mangoes. Are you connected to a mango seller on Facebook? Well, you can search through your friends. The search is pretty straightforward. First, make a list of friends to search. Now, go to each person in the list and check whether that person sells mangoes. Does Alice sell mangoes? If yes, then you're done. If no, then you check if Bob sells mangoes. If yes, then you're done. If no, you check if Claire sells mangoes. If yes, you're done, but if no, you have no friends that sell mangoes. Suppose none of your friends are mango sellers. Now you have to search through your friends' friends. Each time you search for someone from the list, add all of their friends to the list. So if we go back to the beginning when we asked if Alice sells mangoes, if no, you add all of Alice's friends to the list and then check the next person on the list. This way, you not only search your friends, but you search their friends too. Remember, the goal is to find one mango seller in your network. So if Alice isn't a mango seller, you add her friends to the list too. That means you'll eventually search her friends, and then their friends, and so on. With this algorithm, you'll search your entire network until you come across a mango seller. This algorithm is breadth-first search. As a reminder, these are the two questions that breadth-first search can answer for you. Question type 1. Is there a path from node A to node B? Or, in this example, is there a mango seller in your network? Question type 2. What is the shortest path from node A to node B? Or, who is the closest mango seller? You saw how to answer question 1. Now let's try to answer question 2. Can you find the closest mango seller? For example, your friends are first-degree connections, and their friends are second-degree connections. You'd prefer a first-degree connection to a second-degree connection, and a second-degree connection to a third-degree connection, and so on. So you shouldn't search any second-degree connections before you make sure you don't have a first-degree connection who is a mango seller. Well, breadth-first search already does this. The way breadth-first search works, the search radiates out from the starting point. So you'll check first-degree connections before second-degree connections. Another way to see this is first-degree connections are added to the search list before second-degree connections. You just go down the list and check people to see whether each one is a mango seller. First-degree connections will be searched before the second-degree connections, so you'll find the mango seller closest to you. Breadth-first search not only finds a path from A to B, but it also finds the shortest path. Notice that this only works if you search people in the same order in which they're added. That is, if Claire was added to the list before Anuj, Claire needs to be searched before Anuj. What happens if you search Anuj before Claire and they're both mango sellers? Well, Anuj is a second-degree contact and Claire is a first-degree contact. You end up with a mango seller who isn't the closest to you in your network. So you need to search people in the order that they're added. There's a data structure for this. It's called a queue. A queue works exactly like it does in real life. Suppose you and your friend are queuing up at the bus stop. If you're in line before him in the queue, you get on the bus first. A queue works the same way. Queues are similar to stacks. You can't access random elements in the queue. Instead, there are only two operations, enqueue and dequeue. Enqueue means to add an item to the queue. Dequeue means to take an item off the queue. If you enqueue two items to the list, the first item you added will be dequeued before the second item. You can use this for your search list. People who are added to the list first will be dequeued and searched first. The queue is called a FIFO data structure, first in, first out. In contrast, a stack is a LIFO data structure, last in, first out. Now that you know how a queue works, let's implement breadth-first search.